Welcome back for this session this morning. It will be an Italian-oriented session. Well, we'll start with Filippo Fraternali, the impact of galaxy content on this evolution.
Thank you very much. So I'm going to talk about the effect of galactic fountains in the evolution of these galaxies, especially related to the environment around galaxies. When we talk about galaxies, we have always to think that galaxies live in an environment. When I talk about environment, I'm not just talking about satellites, but gas in this case, and this is very important for the evolution of galaxies. We know that these galaxies should be surrounded by a lot of hot gas that forms the corona, and this gas is most probably at the Virial temperature and may extend to the Virial radius. We have now detections of this corona. This is mostly detected in very massive spiral galaxies like this one here, but we also have very nice constraints now for the Milky Way. The corona is supposed, as I said, to be at the Virial temperature. This mass may be a significant fraction of these values. We don't know this yet. But the cooling rate of this corona is probably quite low, order of 0.1 solar masses per year, so it's not enough to feed the star formation in these galaxies. So the thing that I'm going to discuss today is the effect that galactic fountain can have on the corona. And obviously, if you have a fountain going off in the disk, so super bubbles throwing material into the halo, there is going to be a lot of mixing between the fountain and the corona. And this happens in a layer, and this mixing may have several consequences, and the consequence that I'm mostly interested in is the fact that it shortens considerably the cooling time of the corona, and so the corona can increase. So I'm going to show you very briefly what is the global process of this fountain-driven accretion, and then I'm going to focus on some local effects. So we studied this process with hydrodynamical simulations of this kind, where you see fountain clouds that are interacting with the corona, and through this interaction the cloud disrupts and you create a wave. And in the wave there is a lot of condensation from the corona. If you look at the total amount of cold gas in a simulation like this, the cold gas increases. So when the fountain comes back, it comes back with more gas than it went out. Can we look at these things in the data? And the answer is yes. We see it actually very well. This is an example of a galaxy seen age on with lots of neutral gas outside the disk. It is produced by the fountain. And you see that the kinematics of this so-called extraplanar gas is not reproduced by a fountain that does not interact with anything. It's only reproduced by a fountain that interacts and accretes part of the corona. And with a model like this, we can also estimate the accretion rate that we need for this. And the accretion rate turns out to be of the order of the star formation. The Milky Way gives the same picture. In the case of the Milky Way, it is much more difficult to do the fitting, but this is what we have done. I'm not going to describe this, but I just tell you that we have a very clear constraint of the accretion rate through this process in the Milky Way at about 2 solar masses per year, which is, again, very close to the, well, good. It's too much. I asked for some different. So it's very close to the star formation rate. So the conclusion from this part is that the galactic fountain can trigger the cooling of the corona at the disk corona interface, and apparently the amount of accretion that we get through this process is enough to feed the star formation of spiral galaxies. So now I'm going to talk about the local effect of this, and in particular the formation of high velocity clouds, and in particular the complex seas. So high velocity clouds, we already mentioned by James Bachman, they are clouds that are seen around the Milky Way, that they are known since a long time. several mechanisms for the formation of the cloud have been proposed. They come from the IGM, galactic fountain by Bregman 1980, and then many others, satellite, thermal instabilities, filaments. Today I'm going to focus on the prototypical cloud, which is the complex C, this big cloud you see out there. The complex C, we thought a breakthrough was found when in 1999 the metallicity of the complex C was measured. They found 0.1 solar, 10% solar. That's the creation. That was the conclusion. This thing sort of changed it a little bit in the next years, but not dramatically. The metallicity was found to be potentially up to 0.3, and also there were some other overabundance of alpha elements. So what we did, we tried to see, can we produce the complex C by throwing material with the fountain, so explosion of a superbubble in the corona and triggering cooling of the corona. So we effectively we are running an MCMC where effectively we take a superbubble and we move it around in the spiral arms of the Milky Way, considering obviously the velocity of the spiral pattern, and we try to reproduce the data. What data? The data are the emission of the complex C. This is what you see in these channel maps here. So the blue is the emission of the complex C. All the other gray stuff is something else. So you have to concentrate on the complex C, and the red contours are our model. And to make a fit like this is something not trivial at all, because here we are reproducing the shape, the location, and the velocity of the whole complexity, okay, with that model. So now we can see, by the way, we have one single solution, which is the one that I'm going to show you now. So the way to form the complex C is that a superbubble went off here in this Norma Cygnus outer arm about 150 million years ago, and then it threw material in the corona condensed, and here is where the complex C you see now. So now that we have a model like this, we can check it against other independent estimates that we have for the complex C. And the most important one is distance. So these are distance estimates of the complex C as a function of galactic longitude. These are lower limits and upper limits towards of absorption towards halo stars, and our model goes incredibly well through all this data, as you can see. So this data have not been used in the fit at all, because we fit the channel maps. So this is an independent confirmation that this may be exactly what is going on. And then the second thing is the metallicity. The metallicity, of course, starts with high metallicity because it's coming from the disk, but condenses a large fraction of the corona. You see the amount of gas that comes back is more than twice the gas that we threw up. And so what happens is that the metallicity, actually, these are determinations of the metallicity of the complex C as a function of column density, and our model goes through the points quite well. So the conclusion is that we can form the complex C by the explosion of the superbubble that produces the condensation of the corona. So this is a local manifestation of the phantom-driven accretion that I described before. And the last thing I would like to show you is about another high velocity cloud. This is the Smith cloud. This is also well known, and it's been known for many years, and there was no doubt that this was accretion from the IGM. Instead, about a month ago, this was an AGC press release, these authors here measured the metallicity of the cloud, and they found that it's 50% solar. So it's not crystalline accretion. It's most likely, again, mixture between galactic phantom material and accretion. And we have a very, very preliminary model that explains this cloud as a superbubble going off just outside the molecular ring in our Milky Way and causing the condensation that produces the Smith cloud. And this is a movie with our model on top of the Smith cloud. The Smith cloud is the thing that you see below the red contours. Okay, so these are my conclusions. I said that galactic phantom can cool the corona. and feed the star formation into these galaxies. Local features like high velocity clouds can form through the condensation of the corona, and we have a very good fit of this prototypical cloud complex C and promising results for the cloud. The last thing I would like to tell you is a very short hand for this conference that we are organizing in Italy in September. It's a conference just south of Bologna, and in this village here, and to get to that village, you will all have the possibility to cross the route, which is in the middle. And so, the deadline is tomorrow, so if you want to please do it or come to talk to me. Thank you very much.
Thanks a lot. A few questions? Yeah.
Do you have a feeling of how much the metallicity of the cloud decreases when you get material from the core? Do you have a limit on by how much the metallicity decreases?
Well, it decreases. It depends on how long it stays up. So it decreases more and more. So, for example, in the complex C, it goes down more than a factor of 2 from when it started, from a factor of 2 to 3, because the blowout was 150 megayears ago. In the case of the Smith cloud, we haven't done it yet, but it would be less because the blowout was 450 megayears, which fits with the fact that it's a higher.
The same question, what is the final particle range of the gas that is reaccreted onto the disk? And where is it being reaccreted? At what rate is it? The mixture of the fountain and the corona, right? It gets reaccreted, and then the gas that gets reaccreted should have a characteristic that is the balance ratio. And the rate is it when you finally reaccreted? Is the reaccreted the algebra?
Yes, the very good question. So globally, we accrete on the outer parts around 9-10 kiloparsec is the peak of the accretion, but there is a distribution. The peak is there because the fountain is more effective in the outer parts because the potential is lower effectively, so you have less vertical force. And so yes, the idea is that we could, in principle, produce metallicity gradients consistent with what we observe, but I can't speak about that yet.
Is the large mass of complexity a problem?
So the energy that we require to do something like this is 2 times 10 to the 54 ergs. And well, I have this slide to answer your question. If you look at in the Milky Way, we have a similar similar superbubble, which is the Hughes superbubble. In this case, we don't know exactly how much gas it is, but we check that we need exactly the same ejection velocities to produce this one. But if you look at the energy of H1 cores in external galaxies, our energetics is not extreme. So I mean, it's on the high side, but it's not extreme. It should be between 10 to the 53, 10 to the 55.
Other questions? Let's ask people again.